then I'll assume everyone else can too. So I'm going to share my screen here. And okay, can you see that, Michael?
Yes, I can.
Great. So I'm just going to carry on then. And if something comes up, then you can just butt in, Michael, and stop me, and we can address whatever sort of technical issues are going on. I do have two children upstairs who I asked several times in the last few minutes to go further upstairs and play quietly, but you may hear some bumping or screaming from time to time.
All the students are adult learners, so I'm sure a lot of them understand that.
Yeah. So thanks for that introduction, Michael. What I'd like to do today is, exactly as Michael suggested, share with you some of my own data and some of the data that's been collected by the international scientific community that shows us about how the climate is changing, what those impacts are, and try and get at this question of, what is human cause versus what is natural, and how do we know that what's happening today really is human-caused climate change and not some sort of natural cycle. So I'm an associate professor in the Earth Sciences department, and a lot of my research is focused on the polar regions where I look at ice cores, but more and more I've been focusing on the northeast part of the United States, and in particular looking at extreme storms, which I'll talk about towards the end here. So let's jump right in. I want to give you some geological context for what's happening today. And this is one of the really nice things that Earth Sciences gives us, is long-term context for the observations that we have today. So what I'm showing you here is 5 million years of Earth history. 5 million years ago is over on the right here, and today is on the left. And the blue curve here represents temperature. Sort of, you can think of it as kind of a global average temperature. And you can see that there are lots and lots and lots of wiggles up and down, up and down, up and down. And each one of these down wiggles is an ice age. And so our most recent ice age, you can just barely see as the last little down wiggle here. And every up wiggle here is what we would probably call sort of a normal time period, a period that is relatively similar to our climate today. And so there's a couple things that I want you to notice about this graph. One is that over the last 5 million years, if you were to take an average line through these big wiggles, you'd see that over the last 5 million years, we've had sort of an overall cooling trend. And that trend has actually been going on for about 50 million years, not just the last 5, but that we can trace that back 50 to 55 million years in Earth history. But what's most striking, of course, are these wiggles, and which are the ice ages, as I mentioned. We know that these ice ages happen every 40,000 years to 100,000 years. And we know that they are primarily caused by small changes in Earth's orbit around the sun, plus natural changes in CO2. So the way we think about it is that these small orbital changes help start it getting a little warmer or a little bit colder to either go into an ice age or come out of one. And then the natural Earth system kicks in some CO2, quite a bit of CO2, in order to accentuate the warming or accentuate the cooling and put you into an ice age or take you out of one. So if we zoom into the last 800,000 years now, so much smaller time period here. And unfortunately, I apologize for this, but on this one, time is going in the other direction. So now 800,000 years ago is on the left, and time is moving to the right across the screen, and today is here at 0 years before present. And now I'm showing a similar temperature record in red at the bottom. This is from the Antarctic ice cores. And now I'm comparing that to CO2. And some of you may be familiar with a graph like this. A graph like this was featured in Al Gore's Inconvenient Truth movie. And what it shows very nicely is that in Earth's history, temperature and CO2 are very closely linked. Anytime temperatures are high, CO2 is high. Anytime temperatures are low, like in an ice age, CO2 is low. And so this is just like I said, we think that these ice ages that we're seeing here, and again, just like in the previous plot, these cold periods are ice ages, and the relatively warm periods are what we would consider to be sort of normal. These are associated with Earth's orbit around the sun, but then also the CO2 is a key player. And we can see that naturally, CO2 has been ranging from somewhere around 180, and the units are parts per million volume, ppmv. So 180 up to somewhere around 300. We don't ever see CO2 above about 300 over the last 800,000 years. With this context, what's particularly striking is what CO2 is doing now. And so what we're seeing now is that CO2 is over 400. It's over 405 parts per million by volume now. And it's not just that the amount of CO2 in the atmosphere is unprecedented for at least this time period. And we think the last time we had CO2 this high was probably around between 5 and 15 million years ago, the last time CO2 was this high naturally. What's remarkable, though, is just how fast the CO2 rise has occurred. So if you look at these increases in CO2 that happen when we come out of an ice age, those CO2 rises look really fast on this curve. But the CO2 rise that we've had over the last 150 years since the Industrial Revolution is 200 times faster than even the fastest natural CO2 changes. So it's not just the amount of CO2 that's in the air right now that's unprecedented, but the speed at which it's going up is also unprecedented. If we zoom in now just for the last 2,000 years, so today again is on the right. This is now years CE, or AD to 2000 AD, going back to the left is 0 AD. And we can really see that this rise in carbon dioxide, and we can see it also in methane in green and nitrous oxide in black, which are also what we call greenhouse gases. But that this rise is really quite recent. It really did start somewhere around the turn of the 20th century in earnest. So we had this relatively flat CO2 level since coming out of the last ice age, and then all of a sudden with the Industrial Revolution, it's jumped. And as a result of that, the Earth is warming. We know through basic atmospheric physics that CO2 does trap heat that the Earth is radiating. You can think of it as a blanket. A normal blanket that's not an electrical blanket or something doesn't give off its own heat. What it does is it traps your body heat against you. And CO2 does the same thing. The Earth is radiating heat back towards space, and the more CO2 you have in the atmosphere, the more heat gets trapped along the surface of the planet. And so it's like, as we raise CO2 concentrations, it's like we're adding more and more layers of blankets and keeping things warm. And so what I'm showing here is the temperature curve going from the left about 140 years ago now, 1880 AD, and rising up through the middle of the 20th century, and then rising more dramatically towards present day on the right. What's remarkable about this warming is I'm not even showing you the most recent few years. So there's now the most recent few years when we saw temperatures just jump dramatically. Okay, so those last few points are 2018, 17, 16, 15, and 14. So 2014 was a new all-time record, and then 2015 just totally shattered that all-time record. It was actually the biggest jump we had ever seen to a new temperature record. And then 2016 shattered that record. The last 2 years, we've come down a little bit, but these are still 2 of the top 4 warmest years that we have on record. And so if we actually list the warmest 12 years, you can see them here: 2016, number 1, 17, 15, 18, 14, so on and so forth. So clearly things are getting warmer and warmer. And frankly, the warming that we've seen in the last few years, when we saw 2016, it was jarring to the climatological community. And that's not an exaggeration. It was really quite remarkable. How do we know that this warming is from CO2 and that the CO2 is ours? Well, we know that the CO2 isn't coming from something like volcanoes because we humans emit 100 or more times more CO2 than volcanoes do. So there's a misperception out there that you can see on the internet that volcanoes put out more CO2 than humans. It's less than 1% the CO2 that humans put out. More scientifically, CO2 has a chemical fingerprint that proves that it's from fossil fuels. And so the lower plot here has got this funny notation, a delta 13C. And so what this is looking at is the isotopic composition of the CO2. And all that means is that we actually weigh the molecules of carbon in the CO2 to figure out how much carbon-13 is there and how much carbon-12 is there. And it turns out that fossil fuels have a very negative carbon isotopic signature. And so as CO2 goes up in the atmosphere, if it was from fossil fuels, we would expect this ratio to be going down, 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 and that is in fact what we see. More to the point, we know how much fossil fuels we're burning globally, and we can calculate what the isotopic excursion should be based if that's going into the atmosphere and causing the CO2 to go up, and that's what we see. The other thing is that when we burn fossil fuels, of course, we're oxidizing it. We are taking organic carbon, oxidizing it when we burn it, and turning that into CO2. And so what that does is it actually converts some of the oxygen in the atmosphere to CO2. And so what's shown here in blue in the top is actually the amount of oxygen in the atmosphere. And so we would expect that if it's from burning fossil fuels, oxygen levels would be slowly coming down. And in fact, that is what we're seeing. If it was from volcanoes, then we would not see this isotopic change, and we would not see this oxygen change. And do not get alarmed by this drop in oxygen. It looks quite dramatic here, but these are very, very small amounts of oxygen decline. There is plenty of oxygen in the atmosphere. We don't have to worry about suffocation. Again, as I mentioned, we know that CO2 traps heat, and one elegant way to talk about that is that if we had no CO2 in the atmosphere, Earth's average temperature would be -5 degrees Fahrenheit versus the much more habitable 57 degrees Fahrenheit that we enjoy today. So we need some CO2 in the atmosphere to make this planet habitable, and the more CO2 we have, the higher the temperatures go. We see this throughout Earth history, not just during the last ice ages, but people who study deep time, going back tens of millions, hundreds of millions, even billions of years, see this relationship between CO2 and temperature on our planet. So I'm very comfortable adding this to this temperature plot, that the warming that we saw from 1880 up until 1955, maybe 1960, that was from a combination of natural warming as we came out of a period called the Little Ice Age, plus some warming from human CO2. But that the warming that we've seen since 1960 is all from human activities. Not all from CO2, some of it's from methane, some of it's from changing land cover and other human activities, but that is all from human activities. And I can say that because the only other thing that really would be affecting temperature in this way could be the intensity of the sun. And if we add CO2 in blue to this temperature curve, and then we add the intensity of the sun in yellow in the bottom here, we can see that CO2 started to rise coming out of the 1800s. Temperatures started to rise, but notice that solar intensity was also rising. The sun was getting a little bit stronger through time, and we would expect that to cause some warming as well. But notice what solar intensity has done since 1960. It's been going down, 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 at the same time that our temperatures have been going up, 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 along with CO2. So if there were no CO2 in the atmosphere, what we expect, or no human CO2 in the atmosphere, what we would expect to have happened is a slight warming in the early part of the 20th century, and then a cooling since around 1960. And instead, what we've seen is this dramatic warming because of the CO2. There's a nice plot shown here, which is a computer model way of looking at this. And what they've done is run a computer model, a global climate model, that includes natural and human forces. So natural changes in the sun plus human CO2, and that's shown in purple. And you can see that the purple shaded area here matches the black curve, which is what's actually happened, pretty well. But if we remove all the human activity from the climate model and see what kind of Earth that would be, then you get the green curve. And what you can see, it's actually slowly cooling since around 1960, and that's mostly driven by the fact that the strength of the sun has been getting weaker. So again, back here in the early part of the 20th century, it's very hard to distinguish the natural case from the human impacts case. But you can really see that the human impact case diverges starting in the 1960s or into the early 1970s. So that what we're seeing today really is caused by human activities. Another nice little human fingerprint here that confirms that this warming is from greenhouse gases is that the stratosphere is getting colder through time. And the way to think about this is that the stratosphere gets heated up by the Earth too. And so if we are trapping more heat down towards the surface of the planet because of CO2, then less heat is escaping all the way up into the stratosphere. And so again, this is what we would expect if the warming at the surface was from CO2 and other greenhouse gases. If, however, the warming was from, say, changes in the solar radiation or changes in Earth's orbit, then we would actually expect the stratosphere to be warming along with the surface. The fact that the stratosphere is cooling shows us that what we're really doing is trapping some of this heat at the surface that used to escape out towards the stratosphere and then beyond into space. All right, so what about all these little wiggles that we see year to year? Oftentimes I hear people ask, the CO2 curve has some wiggles too, but it's a much smoother increase than the changes that we see in global temperature. So why, if it's from CO2, why don't the global temperature curves look exactly like the CO2 curve? Why do we have these year-to-year wiggles? So let's look at that. A couple of things that we know cause changes in the temperature on sort of year-by-year bases. One is volcanic eruptions. And so these are very large volcanic eruptions like Mount Pinatubo, like El Chichon, Mount Agung back in the 1950s. These are eruptions that spew lots and lots and lots of ash and sulfur, and the sulfur is key, all the way up into the stratosphere. And it acts like tiny little mirrors reflecting some of the sunlight back into space, and it causes cooling. And so what this is showing is that when we have these big volcanic eruptions, we have less radiation reaching the planet, and that causes a short-term cooling. Really big eruptions like this can cause a cooling for a year, sometimes 2.5 years before we come back to normal after the amount of sulfur in the atmosphere goes back down. And so if we go back to our temperature record and kind of zoom in now just in the last 50 or so years, we can see that these periods where we have down wiggles, where it's a little colder than normal for a few years, several of them are associated with these big volcanic eruptions. Okay, so here's Mount Pinatubo, which is the sort of classic case study. Big eruption. We cooled down for about 2 to 3 years here before bouncing back to normal. Agung, Fuego, and Chichon were not quite as dramatic. The other thing that really affects temperature on a year-by-year basis is El Nino. And I'm sure everyone's heard of El Nino. It gets talked about in the news a lot. And all that El Nino is this, it's this oscillation of warm water down in the tropical Pacific Ocean. So what you're looking at is a map looking down on the tropical Pacific. Here's South America and into Central America. And during an El Nino, we have lots of unusually warm water on the surface of the ocean in the Pacific. And then conversely, during a La Nina, we have lots of colder than normal water. It's still the tropics, it's still warm, but it's colder than normal by a couple degrees Celsius. And what that tends to do is that during an El Nino, with all that extra warm water at the surface, it actually tends to warm the whole global average of the planet. And during a La Nina, it tends to cool the whole global average of the planet. Now, that heat is there all the time. It's just either buried deeper in the Pacific Ocean during a La Nina, or during an El Nino, it's up at the surface where it can interact with the atmosphere. So it's not like that heat is disappearing. The reason that we worry about it is because where we measure temperature is the atmosphere. So when that hot water is right up against the atmosphere, it can heat it up. And so we can look at how El Niños have changed through time, and all the red up wiggles here are El Nino periods, if they cross over a threshold of 0.5 here. And then the low blue wiggles here are La Niñas. And so we can see that it kind of wiggles back and forth every 2 to 7 years. We have these things. And so if we go back to our temperature record, once again, we can start to identify the cause of some of these wiggles. In general, the up wiggles are El Nino years, and the down wiggles are La Nina years, exactly as we would expect. Now, you may have heard a lot of people talking about 1998. You'll hear people say, you know, the planet hasn't warmed since 1998. Clearly, that's not true. But the reason they choose 1998 is because that was a very big El Nino year, and therefore temperatures were really unusually warm compared to the overall average. Now, the reason that 2015 and 16 were so crazy off the charts warm as well is also because this was a very big El Nino year. And so we do have to be careful anytime we pick a single year to look at. The best year to compare 1998 to is 2016, because there you're actually comparing apples to apples, a big El Nino year to an equally big El Nino year. And so if you want to know how the global average has changed over the last couple decades, compare 1998 to 2016. Conversely, you can compare La Nina to La Nina years, but what you shouldn't do is compare an El Nino to a La Nina or vice versa. Or the best way to do it is just to put a best fit line right through these, and then you don't have to worry about either one. And that's usually what we try and do. So anytime you hear people pick in a particular year, like a 98 or even like a 2016, you have to be a little skeptical and very careful about what they're saying. All right, so let's look at what's happening locally here in New Hampshire and Vermont. We see very similar pattern here as the global average. In general, we see sort of slight warming through the early middle part of the 20th century, and then a more dramatic warming since around 1960. In general, we see a warming of around 2 to 4 degrees since the turn of the century. Hanover, it's about just over 2 degrees Fahrenheit. And we see the biggest warming so far in the winter. So the winter has been warming faster than, say, the summer has. And that's because in the winter we have relationships with ice. So as we warm up the winter time, we get less snow and ice cover, and that tends to enhance the warming that we get. In the summertime, we don't have anything like that we can sort of accentuate the warming with. So our winters are warming faster, and that's most likely associated with the fact that we have snow and ice in this area. And so why do we care about warming? Of course, warming can be hazardous to health. With increased warming, we see increased heat waves. It is not a linear relationship. In fact, it's non-linear, meaning that we expect to see a lot more heat waves with even a small increase in average temperatures. Tragic example of one of these heat waves would be the 2003 heat wave in Europe, where at least 35,000 people died. Some estimates have it higher than 50,000 people. And the research confirms that we would expect to see more intense, more frequent, and longer lasting heat waves into the future associated with climate change. And that's just related to the statistics of how when you warm just a little bit, you get a lot more of these extremes. We can see more recently the 2010 Russian heat wave and fires. There were confirmed over 50,000 deaths in that. Okay, and a lot of these were from cardiac and respiratory distress, which often happens during our heat waves. Here in New England, there was a really nice study done by the Department of Health folks, the state of Vermont, and they were interested to see at what temperatures do we start seeing people go to the emergency room more frequently complaining of health-related illness, or sorry, heat-related illness. And you might expect that it's, really warm, so something up in the high 90s or something. And what they actually found is that even in the high 80s, once you get temperatures close to the high 80s into the low 90s, you already start to see increases in the number of emergency room visits associated with heat stress. And the population that tends to be most vulnerable are it's what we call bimodal. There's two main groups. It's the younger folks who tend to have jobs outside, and they're therefore exposed to that higher heat. And then it's older folks who often have other medical conditions that are easily exacerbated by the heat. So folks that already have respiratory or cardiac conditions, you have warmer temperatures, maybe you don't have access to air conditioning, and you can see exacerbation of those pre-existing illnesses. Another thing that I've been studying here at Dartmouth is the relationship between climate change and Lyme disease. We have seen a dramatic increase in Lyme disease in Vermont, New Hampshire, and northern New England in general. You can see these two CDC maps on the bottom. In 2001, this is the extent of the reported case of Lyme disease. And then in 2013, you can see just how dramatically those cases have increased in northern New England. This trend has continued all the way up through the latest data in 2017 that I've seen. I'm not showing that here, but this trend has continued on. Now, part of this is that folks are being more aware of Lyme disease. And so some of this is simply due to the fact that people are diagnosing it more frequently. But the vast majority of this is because there are actually more incidents of Lyme disease. My wife is a pediatrician, and she started her training here at Dartmouth Hitchcock as a resident in 2007. And when she first started her training, it was fairly unusual to get a case of Lyme disease walking in the door. And now she's a physician at Alice Peck Day Hospital, and pretty much every day in the summer, she's walking into her clinic room and finding a case of Lyme disease, including my 8-year-old son had Lyme disease a couple years ago. It's just, it's everywhere now. And it's because we have warmer winters, as we mentioned, and that allows these black-legged ticks to survive. They are extremely sensitive to freezing temperatures. And so if we have more really, really cold nights in the winter, we're more likely to kill off a lot of these ticks and reduce the numbers of them. And when we have fewer of those really cold nights in the winter, then those ticks are more likely to survive and breed, and the population increases. Another tick story, which is really upsetting, and I didn't really believe it when I first heard about it, but it's shockingly true, is another kind of tick. This is called the winter tick. They are also thriving in these warmer winters to the point that they're having a huge effect on the moose population of northern New England. Up to 70% now of New Hampshire moose calves are dying from tick infestation. And so what happens is these winter ticks are reproducing at much higher rates and are covering these moose calves who are particularly susceptible to that very first winter. And it weakens them to the point that if they're just a little bit late in finding a good meal, and finding new food in the springtime, then they often don't survive that very first winter of their life. It's quite dramatic. All right, I want to talk a little bit about the Arctic, because I do quite a bit of work in the Arctic. When we look at climate change, when we look at how temperatures have warmed, it is not uniform across the globe. We have seen about twice as much warming in the Arctic region as we've seen in the rest of the globe. You can see lots of purples and sort of dark reds up here. Those are about twice as high rates of warming as we've seen, say, in most of the United States. And we term this Arctic amplification of global warming. And again, it's related to the fact that you have lots of snow and ice up in the Arctic. And so small increases in temperature cause not just warming, but also melt the ice, which causes further warming. And so you have this self-reinforcing cycle. You have this positive feedback that accentuates the warming in places with snow and ice like the Arctic. Something that you're probably fairly familiar with is the decline in Arctic sea ice. This is typically, we measure it all year round, but when we talk about this, usually we're talking about the summer minimum in sea ice. In the wintertime, the Arctic is still covered by sea ice, but what we're seeing is that every year in the winter, we get less and less sea ice forming, and every year in the summer, we get less and less sea ice surviving into and through the summer into the next year. And so what you can see here is the black line shows where sea ice used to be back in the 80s and 90s during September. And then the previous record, which was in 2007, is shown in yellow. And then the second most recent record, which was in 2012, is what's actually shown here. And I've got a little animation that I might try and show you here. I hope this works.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older
we can
ice.
hear it, but we can't see it.
Oh,
That's the
okay,
voice
hold
of
on.
Dr. Walt Meyer.
Let me, you know what? I'm not going to risk showing all that.
Okay.
Sorry about that, folks. But basically, what's happening here is that we don't just have a decrease in the amount of sea ice, but we have a decrease in the sea ice thickness and the sea ice age, which is another one of these self-reinforcing cycles. So it's not just that it covers a smaller area, but it's much thinner and therefore easier to melt the next year. And so as a result, sea ice has been declining really dramatically in the Arctic. Again, the years that I showed there were 2007 and then the new record in 2012. This overall trend, you have to, again, always be careful of these little wiggles. What I prefer to look at is the overall trend. There are some projections that sea ice will be, the Arctic will be sea ice free in the summertime, again, in the summertime, within about 15 or 20 years. And that has huge implications, not just for the ecosystems, for polar bears, for other ecosystems in the Arctic, but also for, of course, commerce, for shipping, for exploration, for drilling, all sorts of things, okay? Major, major implications geopolitically, economically, and ecologically in terms of this change in sea ice. I mentioned that I do a lot of ice core research, and one of the recent projects that we did was a two-season snowmobile traverse of Greenland in order to figure out just how fast Greenland ice sheet is melting. And so what I'm showing here is a map of the route that we took. This was around 5,000 kilometers of snowmobiling that we did. In 2016, we started at this lower star called Die 2, and over about 2 months, we made our way all the way up to Summit. And each red dot was an ice core that we collected, and all the black lines show where we collected radar data over the glacier that allows us to see the annual layers of snowfall in the glacier and see layers of melt. And so that was 2016, and then 2017 we started at Summit, and then we made a big circle and ended back up at Summit and collected 9 more ice cores shown as these red circles. So it was a really logistically intense and kind of ambitious field campaign that we tried to do, but we wanted to do it because this is a critical area of Greenland. We know that this area is melting fairly quickly right now, and we wanted to understand just how fast it's melting and see the long-term context for that melt. And so to give you a sense of what this looks like, I mentioned we were collecting radar data. That's what's shown at the top here. So the little antenna is a GPS unit, so we know our position, and then we're dragging, actually, I think we had about 5 different radar systems that were collecting data on these sleds here. And that's one of our graduate students there. And each year we had 5 team members. I led one year in 2016, and my colleague led another year in 2017. And so we're totally self-sufficient out there. All the camping equipment, all the scientific equipment, all of our food, our survival gear, and everything is all with us at all times. We had 2 little safety pods here in case the weather got really bad, too bad for our tents. We could always retreat to the safety pods. We never had to do that, though. You can get a sense of the work here. So you see 2 big tents in the background. Those big yellow tents are our kitchen tent and our science tent. And then here are 2 of my graduate students collecting an ice core. The one in the back here is actually drilling the ice core, and Karina in the foreground here is analyzing the core and measuring it and weighing it. And so this is what we did at each one of those red dots, 16 cores in total. And what we're looking for is these are, you're looking at an ice core sort of on its side here. And the dark grainy kind of stuff is what a typical ice core looks like from Greenland. And this lighter stuff is what it looks like when you get melt on the surface, and then that melt water trickles down into the snow and then refreezes as a solid ice layer. And so these will turn into sort of bubbly ice. The regular grains that aren't affected by melt will turn into bubbly ice. And where you get melt and refreeze, you can see there are no bubbles. And so it's very easy for us to tell the difference. And by doing this, we can figure out just how many melt events there were in the summer, going back through time, and how much melt occurred during those events. And this is just gives you a sort of an aerial view of what it looks like for us. So you can see those two yellow tents again, our kitchen and science tent. We've got our little refueling station back here. And then we have 1, 2, 3, 4 personal tents for sleeping. And one of us decided he wanted to just sleep in a pod. So he was sleeping in that pod back here. We line them up like this because the wind is coming from the left part of this picture. And that way we don't drift each other in. You can see the little drifts on the backside of the tents that caused by the storms that blow through. And then when we do our research, we do that upwind of the camp so that we're not contaminating the ice core site with our own fumes from our snowmobiles or our cooking or anything like that. And so this is what we found. If you look at the amount of melt that we see in the ice cores through time, what we found is that the amount of melt that we see today on the right-hand side here is unprecedented for at least 450 years. Okay, the deepest ice core we were able to get went back 450 years. And what we know from other data collected by other researchers around the Arctic is that most likely we haven't seen melt like this for at least 7,000 years. And so you may ask yourself, well, what was happening 7,000 years ago? There were no people driving around cars. We didn't have human CO2. But that was one of those times where, because of Earth's orbit, the Earth was naturally about as warm as it is today because of little changes in Earth's orbit. But we know that those changes in Earth's orbit are not responsible for today's warming. It can't be because it's way too fast, and it can't be because we know what the Earth's orbit is doing. And right now, based on Earth's orbit, we should actually be cooling, not warming. And this is not just Greenland that's melting. I'm sure you've had the impression that glaciers are melting around the world, particularly mountain glaciers. And here's a glacier I go to every year. This is the Athabasca Glacier in Jasper National Park in Canada. And I take students to this glacier to teach them how to do this kind of research because this is probably the most accessible glacier in the world. There's a parking lot right down here, and we can walk right up to the glacier. And so on the right is what this glacier looked like about 100 years ago in 1917. And what I've done is scale these two pictures so that they're the same scale and basically the same aspect. If you were to overlay the two, you would see that the mountains in the background overlay each other perfectly. So not only has the glacier retreated backwards up the mountain, but it's also thinned dramatically. And you can really get a sense of both of those things happening. And so anytime you see something like this, you should be very curious. Is this a cherry-picked glacier? Is this one that just happens to be melting really quickly? Or is this representative of what's happening around the world? And so for that, we have to do much larger studies. And this is a study that was published in Science or Nature, I can't remember which one, back in 2013 by Gardner and colleagues, showing that every red dot here represents glaciers losing mass. And what they found is that these small, quote unquote small, so these are glaciers in mountains basically, that these mountain glaciers are melting in every region of the world. There's nowhere in the world you can go and find that the glaciers are advancing today. You may find an individual glacier that is advancing for some strange glaciological reason. But if you take all the glaciers in a particular area, they are shrinking on average. And any glacier that's advancing today will soon be shrinking. So it's not just a cherry-picked example on the Athabasca. This is representative of what's happening worldwide. And these glaciers have about 2 feet of sea level rise in them. There's a lot more sea level rise trapped in Greenland and Antarctica where we have the big ice sheets. And so let's look at Antarctica. That's another place where very recently, just in the past few years, there's been a lot of publications coming out showing that western part of Antarctica is also melting pretty dramatically. There was a pretty dramatic headline from 2014 that at this point Antarctic ice sheet melting might be unstoppable. That is very much up for scientific debate, but what is not up for debate is that the melting is occurring. What's interesting is that in Antarctica, it's not being driven, the melting is not being driven by warm air temperatures. It's still cold enough in Antarctica that the air temperatures aren't really affecting the glaciers. It's the warming ocean temperatures that are melting Antarctica from beneath. When you compare that to Greenland and the mountain glaciers, it's not the ocean that tends to be melting it, it's really more the air temperatures. But either way, we have warming atmosphere and warming oceans, and they're both causing shrinking of the two ice sheets. And so as a result of that, of course, sea level is going up. A lot of people may not be aware that sea level has already gone up about a foot in the East Coast of the United States and about 7 to 8 inches globally since around 1900. Today's rate of rise, so the rate of sea level rise over the last couple of decades, say from 1993 to 2010, the average today is around a foot per 100 years. But you can see if we look at the rise through time that the curve is starting to bend up. So the sea level rise rate is increasing through time, and we expect that to continue into the future. We can see examples of this in some of the major metropolitan areas in the East Coast of the US in particular. So what I'm showing here are plots showing the number of hours each year where water is particularly high in New York City and in Norfolk, Virginia. And again, you can see that this is just during big high tides, essentially. Big high tides that are accentuated by a full moon or a new moon, that we see more and more and more times when the water is really high in New York and in Norfolk. And so what does that look like? It looks like this. It's what we call fair weather flooding. This is very common in Miami, Florida. It's now almost commonplace in Miami, Florida, that during spring tides, so large high tides, you have huge sections of the city that are now just flooded, even though there's no storm going on, there's no rainfall, this is just sunny day flooding. Same sort of thing is happening in Annapolis, Maryland. I was just listening to a radio piece the other day about this happening along the National Mall in Washington, D.C. More and more sections of that, they just have to build seawalls because they're slowly going underwater, not during storms, just during regular high tides now. What's interesting is that if we look at the rate of sea level rise, it's actually, we have a little bit of a sea level rise hotspot on the East Coast of the United States compared to the global average. So as I said that over the last century, global average has been about 8 inches. And we can see that 8 inches shown in the lower plot from, say, Florida, where that's sea levels rising in Florida at about the same rate as the global average. But in the top plot, you can see what Norfolk, Virginia looks like. And other areas in the Chesapeake Bay, going down to North Carolina, all the way up to Boston, look very similar to this, where you're seeing almost twice as much sea level rise over the last century. And so you may be asking, like, what's going on the mid-Atlantic coast of the US? And essentially, what's happening is that global sea level is going up because the glaciers are melting and the oceans are warming. And at the same time, this part of the eastern seaboard is slowly sinking down. And so those two things together give you a local sea level rise that's about twice as fast as the global average. And the reason that this land is sinking is two-part. One, because we're extracting a lot of groundwater there to support these major population centers. And two, because the Earth is actually still sort of getting back to normal from the last ice age, when we had an ice sheet here in Hanover that was a mile thick, and that ice sheet extended all the way down to Long Island. And so when the ice sheet melted, the Earth slowly rebounds, rises up where the ice sheet used to be, and then further south, so the ice sheet made it down to Long Island, but further south below that, the Earth was bulged up when the ice sheet was there, and now that the ice sheet's melted back, the land is sinking back down. So it's a couple different things happening here, but the net result is that whenever you see global sea level rise estimates, you have to increase them if you're living somewhere here in the eastern seaboard of the US, where it just so happens we have these major metropolitan centers. So the last thing that I want to talk to you about is extreme storms. And this is something that I've been researching just for the past few years as a new colleague came to Dartmouth who was also interested in this, and we really started a research program looking at this. And our research program was sort of spurred by this figure, which is fairly well known now in climatological circles. It's a figure from the National Climate Assessment Report that came out in 2014. And that report, if you've ever heard of the IPCC report, which gives the latest and best data about climate change around the world, the US Climate Assessment Report is like the IPCC, but just for the United States. And so it's all the best climatological data that we have about what's happening in terms of climate change in the US. And what this shows is that the amount of rainfall that was occurring during extreme storms jumped in the Northeast by 71% from 1958 to 2012. And you can see it also went up in other parts of the United States, but nowhere did it go up as much as the Northeast. And this really struck me because I've been living in the Northeast since 1977, and that's a big number. And so we really wanted to dig into that, find out if that number was cherry-picked, find out why that number was happening, whether we can really trust this number. And so we decided to really dig into it. We took 116 weather station records from around the Northeast, going all the way down to West Virginia, all the way up to northern Maine. And you can see the location of each of them here with a dot. And what we did is we only picked the very best weather stations, the ones that were missing very, very little data, and the ones that had very high quality data of precipitation rainfall. And so we looked at that, and we looked at just the extreme rainfall. And when I say extreme rainfall, I mean when we have a storm that dumps, say, 2 inches or more in a day, or 3 inches in a day, that's what we're calling extreme rainfall. And what we're seeing, if you remember, they said that there's been this 71% jump since 1958. And what we found is that there really was no change in these extreme storms all the way up until 1996. And then in 1996, there was a jump. And that jump was more like a 53% increase. But what was remarkable was just how abrupt this jump was to what appears to be, at least through now, a new normal. And so since 1996, we've been getting a lot more extreme rainfall associated with extreme storms. So these are the kinds of things that we get during, say, hurricanes or really, really intense thunderstorms. So this was a little bit of a different twist from the initial figure, which suggested maybe like a linear increase through time. It wasn't a linear increase, it really was a jump. And so it begged the question, what the heck happened in 1996? And what's been going on since then? The other thing we wanted to know is, why was this happening? So what kind of storms were driving it? And I'll just give you our take-home bullet points here. We found that about half of that jump in 1996 was due to more hurricanes coming all the way up the East Coast and dumping lots of rain on the Northeast. And so the classic example of this was Hurricane Irene in 2011. What we found is that what's fueling this increase in the hurricanes is warmer ocean temperatures down in the tropics where the hurricanes come from, and more water vapor in the atmosphere, which is what we expect to happen when the temperature goes up. So warmer temperatures can, you probably heard, warmer temperatures hold more water vapor in the atmosphere, or can hold more water. And that water vapor is like gasoline for these hurricanes. And so with more water vapor in the atmosphere, when a hurricane does form, it can get more intense and dump more rainfall. And that's what we've been seeing since 1996. We found that about a quarter of this jump was due to really intense thunderstorms associated with cold fronts. And we've had a couple of examples of these kinds of events just in the past few years here in the Upper Valley. So on July 1st, 2013, we had about 3 inches of rain hit Lebanon, New Hampshire. and we had what many of us refer to as the Slayton Hill landslide, Slayton Hill slide, or Slayton Hill flood, where this new condo townhouse community was flooded and inundated with sediment because the culverts weren't quite large enough to handle this much water. We had another thunderstorm just last year, July 1st, 2017, and that wiped out lots of roads up in Orford, New Hampshire, Thetford, Vermont, and that sort of region. And so these are the kinds of events that we've also seen more of, and that represents about a quarter of that jump since 96. And so what's been happening since 96 for these guys is that we seem to have a wavier jet stream. And a wavier jet stream tends to give us more of these summertime cold fronts, which is what gives us these really intense summertime thunderstorms. And then the last 15% of the jump in 1996 and in these extreme storms seems to be associated with these nor'easters. And the nor'easters, a nice example would be the 2007 President's Day nor'easter, where eastern New Hampshire and western Maine just got totally dumped on with lots and lots of rainfall.
Eric,
yeah.
Could you explain what a nor'easter is to our people in California?
Yes, sorry. So nor'easters are, these are extratropical storms. We call them extratropical cyclones. They're these big comma-shaped storms that you'll see on the Weather Channel. They tend to form down off of, say, South Carolina and make their way up the coast. And in the wintertime, they give us these big snowstorms. Maybe we get a foot of snow. And in the summer, spring, and fall, they give us really intense rainfall and wind. So they're not the same as tropical storms, but sometimes they can be almost as powerful as tropical storms. And so around here, we call them nor'easters because when they hit, we get the wind coming out of the northeast. And so these are also caused by a wavier jet stream. And again, what we've seen is the jet stream is getting wavier and wavier through time, especially since 1996. And so let's look at that a little bit. This is what I mean by a wavier jet stream. What you can imagine is that the jet stream used to look more like the red. So there were waves in it, but the waves were not as big as they are now, which is depicted in the orange. And of course, this is a cartoonized version. It's a little dramatic, but this is the idea, and the data supports that this has actually happened, that the jet stream has become wavier and wavier. And why that matters is that a wavy jet stream gives us more storms. It gives us more of these extreme storms like nor'easters, and it gives us these extreme thunderstorms in the summer. By the way, it also gives us more heat waves in the summer, and it can give us more things like droughts in the summertime as well. And so why would that be happening? Well, we think that it's happening because of that Arctic amplification I mentioned, the fact that the Arctic is warming faster than the rest of the globe. And so what drives the winds and what drives the jet stream are temperature differences between the equator and the pole. So the larger the temperature difference, the faster the wind blows. And so you can imagine that it used to be the fact that the equator was really warm, the North Pole was really cold, and so there was a big temperature difference there, and so the jet stream was very strong. Now, with global warming, the tropics have gotten a little bit warmer, the Arctic has gotten a lot warmer, and so there's a smaller difference between them. And what that means is that the jet stream has slowed down, and when it slows down, it gets wavier. Okay, so the link here is that Arctic warming causes the jet stream to slow down, and when the jet stream slows down, it gets wavier, and when it gets wavier, we get more extreme storms. This is something that is sort of cutting edge in climate change research. The first papers to come out about this, I'm citing the most famous one here from Francis and Vavras in 2012. So this is just in the last 5 or 6 years that we've been really focused in on this. But I think it's a huge advance for us because it draws the connection between large-scale climate change and weather, right? And the way we experience climate change as humans is through weather. Nobody experiences a 4-degree global average temperature. What they experience is the weather at their house or in their town where they live. And so the jet stream is a connection between these two things. And we're just starting to really understand that better. So here's some examples of the kind of things we're talking about. So with the warming ocean temperatures in the tropics and the more hurricanes, we had that record-breaking hurricane season in 2005 where we had 28 tropical storms. We actually ran out of letters to name them. We had to go into the Greek alphabet in 2005. That had never happened before. In 2012, we had Hurricane Sandy, which was an extremely, extremely unusual storm, not just because it was so big and so intense this far north, but because it took a left-hand turn into New Jersey when normally it should have headed off to the east, out into sea. And interestingly enough, that was caused by a big wave in the jet stream. Very, very damaging, of course, a very damaging storm. 2017 was a record-breaking hurricane season in terms of the number of huge and devastating hurricanes that we saw coming through, including, of course, Hurricane Harvey, dumping the most rainfall we had ever seen dumped ever before down in the downtown Houston area. And then I haven't even made a new slide for it yet, but this past 2018 season with Hurricane Florence and Hurricane Matthew, both Category 4 storms, Hurricane Florence, again, dumping immense amounts of precipitation, amounts of rain, and then Hurricane Matthew getting extremely intense very quickly. It's not that we didn't used to have big hurricanes. It's that the big hurricanes today dump more rain because there's more moisture in the atmosphere because the atmosphere is warmer. And these storms get more intense more quickly than they used to. And a telltale sign of this is that you'll see the forecasters talk about these hurricanes now, and they'll say, oh, we expect it to strengthen to a Category 2 overnight and maybe a Category 3 by the next day. And then you wake up the next morning and it's a Category 4. And that's because some of these forecasting rules of thumb that they've had for decades don't apply anymore. With the ocean so warm and this much water vapor in the atmosphere, as I said, it's like gasoline for these things. And they're becoming more powerful more quickly than they used to. One of the things I really want to dig into more are these big nor'easter storms I mentioned. So here's 4 nice examples. Just this past March in 2018, we had 4 of these really big storms hit Boston in just a 3-week period in March 2nd, 7th, 13th, and 21st. It's very, very unusual to have that many storms in such a rapid succession, but they were all associated with this really big waves in the jet stream. And that was after an even bigger one that had just happened a couple months earlier in January 2018. This is what it looked like in downtown Boston. March 2nd, a particularly ironic photograph. This is a informational placard down along the coast near the New England Aquarium in downtown Boston on the harbor, showing, talking about climate change and rising seas in Boston Harbor. And sure enough, you can see the effect here. That January 4 storm was the highest flood levels they had ever seen in Boston, caused over $1 billion in losses, and it was about 4.5 feet above the high tide line. And you can see what that meant. This is flooding in downtown Boston. These are firefighters. These are flooded streets that then froze because, it's in January 4th. It was very cold at this time. So it made for just really miserable conditions and over $1 billion in economic losses. And we've seen the same sort of thing here locally in New Hampshire, where we're seeing more of these very costly in terms of dollars, natural disasters. And if you look down through this list around here in the Northeast, almost all of these are from floods. So this is the sort of activity that we've been seeing more and more of. And in fact, you can even see that change point in 1996 that I talked about, right? There's not a whole lot happening before 96, and then a lot of these events after it. So I wanted to just wrap up. I didn't really talk much about future climate. I'm trying to focus more on what we've already seen, because those are data that you can hang your hat on. This is all real. This is happening, and we understand why it's happening. As we look to the future, so much of it really depends on what the global community decides to do about CO2 emissions. And so, under a business as usual scenario where we continue on as we have been, we're looking at temperatures close to 8, sometimes even higher than 8 degrees Fahrenheit warmer by the end of the century. And 8 degrees may not sound like a lot. I can imagine somebody saying, well, yesterday was 8 degrees warmer than today, so who cares? To give you some context for just how big of a temperature change that is, the last ice age that we had was 8 degrees colder than today. Okay, so an 8-degree shift in temperature was enough to take New Hampshire from today, what it is like today, to having a mile of ice on top of it. So these are really huge changes when we're talking about the global average. Under lower emissions, then we're looking at smaller increases in temperature, more like 4 degrees Fahrenheit. And then, of course, sea level rise. This is for Boston, but these numbers are not too dissimilar. The different curves, again, the red curve represents business as usual. The green curve represents pretty dramatic cutback of emissions. And then the blue curve represents probably unrealistic cutback of emissions. And so, the decisions that we make about carbon emissions will continue to matter. However, disruptive sea level rise, disruptive increases in temperature are going to occur regardless. That doesn't mean that we can't reverse it into the future at some point, but we will have to continue to struggle with some of these changes in climate for several decades into the future, even under the most stringent reductions in CO2. And so really this calls for a combination of what we call mitigation and adaptation. Mitigation meaning we have to reduce dramatically the amount of CO2 that we put into the atmosphere, or start actively sucking the CO2 out of the atmosphere. And then adaptation, we have to get prepared to deal with these things, knowing that they're going to happen, they're already happening, and they're going to continue to worsen into the future. So both mitigation and adaptation. And just to kind of bring this home, here's this picture again. So that 4.5 feet of storm, this caused over $1 billion in losses here. That was, the 100-year storm that happened just last year, but that could be every day in 2100. In Boston, we're expecting 4 to 5 feet of sea level rise. So rather than being this unusually intense storm, this could be every high tide in Boston. And with that, I'm happy to take any questions that you folks have from the audience.
Okay. Actually, some people were typing questions to me while you were speaking, so I'll deal with them. But if you have a question, just put your name into the chat and send it to me, and then I will know that you want to unmute your microphone. But let me ask the questions that did come in, Eric, and
sure.
Keep your screen on, because the first one was asking about your graph of carbon-13. Was that a ratio of carbon-13 to carbon-12, or was that just carbon-13 that drop?
No, that is a ratio. What that delta notation means is that it's a ratio. And so these units, it's listed as per mil. The units are really convoluted. The way that these numbers are calculated is pretty complicated. I spend a whole lecture usually teaching my students this. But the bottom line is that down means that we have this fossil carbon fingerprint in the atmosphere. And the isotopes really convincingly show that. So
you're saying the carbon-13 is in the denominator?
No, in this case, the carbon-13 is in the numerator, and it's the carbon-12 that is enriched in fossil fuels. And so if we have a lot more of the fossil fuel stuff, we'd expect more carbon-12 than normal. So basically life likes the lighter carbon. A carbon atom is a carbon atom to life. So if you can choose one, it's going to choose the lighter carbon-12 instead of the heavier carbon-13 because it takes less energy to do something with that. So fossil fuels, which are made out of, bits of things that used to be alive, have a lot more carbon-12 in them than you usually find in the environment. And so when you burn them, all that carbon-12 is getting put into the atmosphere, and we can see that as a declining carbon-13 to carbon-12 ratio. Does that make sense?
Yeah, that makes sense, and I think that answers that question. Another question is that you use the term cherry picking a lot through your term, and so as as non-scientists are talking to policymakers or even community decision makers, how do they know when they're looking at information that's not cherry picked? Or how would they find out?
So what I guess I would suggest to people, I think the bottom line is that it can be difficult because this issue has become so politicized that people are all too eager or have no problem with showing cherry-picked or skewed data to support their line of argument on either side of the issue. And so anytime you see somebody, pointing to an individual year on either side of the argument, I would be skeptical. Anytime you see somebody pointing to any particular location, right? You'll see somebody, oh, look at this one graph of this one place. The climate doesn't really work that way. We need to be looking at long-term averages and long-term trends. And so I don't like to look at any one place or at any one time and say too much about that. So that might be one thing that people can kind of be a little wary of. Like you'll see CNN will often show, an individual big chunk of ice fall off of Antarctica, a big iceberg fall off Antarctica, and they'll make a lot of hay out of that. And of course the question is, well, don't healthy glaciers do that too? And of course they do. And so that information that a big iceberg fell off Antarctica doesn't really tell you anything. What you need to know is, how unusual is that, right? Is that happening more frequently? And is that part of a larger trend? And so I think we just need to be a little critical. And anytime you see somebody picking out specific years, it's probably for a reason, because they're trying to accentuate their point, which frankly is why we were so skeptical of that that increase in extreme rainfall from this plot. I thought it was really weird that they chose 1958. Why not 1950? Why not 1960? Like, why 1958? What a strange year to pick, especially when I know that in the early 1960s was the biggest drought of the 20th century here in the Northeast. And so if you start a trend in a really, really dry year, then sure, you're going to accentuate that trend. It turns out that this number is not actually cherry-picked. I said that our preferred number is 53. But if you actually calculate this number correctly, they did it a little bit wrong, but the correct number is more like 103%. So they were wrong, but they were wrong on the low side, not on the high side. And but as I said, I think the better way to talk about it is like this, because there really was no trend until 1996, and then it jumped up. So it is hard. I hear you. It's very hard for people who aren't experts in this to know what to believe. But warning signs are when people talk about a specific year or a specific place as an example.
Okay, great. I had two questions around hurricanes.
Yes, great.
Okay, one was someone had heard that there really is not a scientific consensus that the way I interpret it is the intensity and frequency of hurricanes being increased is due to climate change. I mean, the science isn't there yet.
So I'm not surprised that you've heard that, because the science on this has been controversial for a couple of decades, and only very recently, like the last 2 or 3 years, have we gotten to a place where the science is confident in looking at individual storms. So one way to look at this is the trend. And you can ask yourself, do we see a trend in more hurricanes? And do we see a trend in more intense hurricanes? The answer is we do not see a trend in more hurricanes. What we see is a trend in them being overall more powerful. And that doesn't just mean like, do they reach category 4 or do they reach category 5? There is a big difference between a storm that is a category 5 for 10 days and a storm that's a category 5 for 1 day, right? The one that's a category 5 for 10 days is a lot more powerful. And so if you look at the storm's intensity and incorporate how long it's at those intensities, we see a pretty dramatic increase in the overall power of these storms through time. What we think is going to happen in the future is that we will probably have fewer small hurricanes in the future, and perhaps even fewer numbers of hurricanes overall. But that when we do have hurricanes form, because the ocean's so warm and because there's so much water vapor in the atmosphere to fuel them, they will become more powerful. So we'll see more of the most powerful and damaging hurricanes, the category 3, 4, and 5. Even if the total number goes down, we'll see more of them total. And that seems to be the consensus now, and that is consistent with what we've been seeing lately. And like I said, very recently, people have been looking at individual storms like Hurricane Harvey. You'll see papers coming out on Hurricane Florence and on Hurricane Matthew from last year, where they can look at the statistics and say, without climate change, how much rain would Harvey have given us? Or how likely was Harvey in a natural world versus how likely was it in a human influenced world? And so that science is brand new, but it's all statistical based. It's almost like insurance kind of statistics. And it's very convincing that human activities are having an impact on these storms.
Okay. I have one more question that someone typed, and then there's a couple of people who are starting to want to ask questions. So what is I've heard about this carbon black impact in Greenland. Can you explain what that is?
So when ice melts, anything that's in the ice gets concentrated on the surface. So you can imagine dust, you can imagine forest fire soot gets concentrated on the surface, and it'll make the surface go from white to darkish. And everybody's experienced this if they've seen, fresh snowfall. You go outside right after a fresh snowfall event, and it's like blindingly bright. And then a couple days later, that same snow is still there, but it's not nearly as bright. And so that's because as the snow melts a little bit, you get some of these impurities concentrating on the surface. So the same thing happens in Greenland. And as Greenland melting accelerates, we have concerns that the surface darkens quickly, and that accentuates melting. And so it's one of these self-reinforcing or positive feedback cycles where as the surface gets darker, it melts more. The increase in melt causes it to get even darker, which causes it to absorb more solar radiation and melt more, which causes it to get darker, and so on, so on, so on, so on. So there is convincing evidence that Greenland is getting, the surface of Greenland ice sheet is getting a little bit darker, and that does have an accentuating impact on the melting. But it is something that a lot of people, myself included, are trying to study more and more, because exactly how much of an impact it's having is hard to say. Okay.
I'm going to open it up. I got a question from Christopher. Chris Rogers, you want to unmute and ask your question if you can? And then mute afterwards?
Yeah, sure. Thanks, Michael. And thank you, Eric, so much for this very informative talk on your time. About 12 years ago when I was in undergrad and took a climate change course, we studied a book by Dr. Richard Alley, The 2 Mile Time Machine. And maybe you're familiar. And I was just curious, I think that his data, he was, with their technology at that time, they were able to get data of about 2 million years. And maybe I'm wrong. But I think in one of your first slides, you showed about 5 million years of data. And just curious if the technology has changed in this realm over the last decade or so, or if you can speak to that at all. And
So Richard Alley is a very well-known and highly respected, included by me, ice core scientist. And so most likely the data he was showing you was ice core data. And the deepest ice core data we have is shown here is 800,000 years. We can go back basically 8 ice age cycles with the ice cores. We are trying to get, we think there is million-year-old ice in Antarctica and probably even 2 million-year-old ice in Antarctica, but we haven't been able to collect it and analyze it yet. The longer-term data I showed here going back 5 million years is not from ice cores. This is from ocean sediment cores. And the ocean sediment core record actually goes back 80, 100, sometimes 200 million years. And so I'm just showing you the very top, if you will, the most recent 5 million years of the climate record that we have from the ocean cores. And so what's nice is that over the period of overlap, so over the last 800,000 years, the ocean cores and the ice cores look very, very similar. So we have confidence that they are both giving us a really nice representation of the climate. But so nothing has really changed dramatically in the past decade in terms of how far back we can see. These ocean core records have been around for decades. The ice core records a little less, but I think Richard probably would have been talking about those ice cores.
Okay. I'll turn this over to Shamika, if you can turn on and ask one of your questions.
Sure. I'll just stick with the first one. So thank you again, as Chris said, for being here and speaking with us. I actually wanted to know what, if any ideas you had about geoengineering, and if you agree with it, disagree, if you think that we could like geoengineer our way out of the problem. I have my own opinions, but I think it's good for others to hear it, because I feel like people think there's like this save the day, we're going to like engineer our way out of it kind of idea.
Yeah. So it really depends what you mean by geoengineering, or not just you, but people use that term geoengineering to mean all sorts of different things. I'll tell you the way I think about sort of overall solutions right now to this. If I were president or world emperor or something, what I would try and do. I am more and more convinced that it's going to be a all of the above approach, that we have to do pretty much everything that people are talking about to some degree. So that is, reducing the energy we do use through efficiencies. It is changing our mix of energy so we have much more renewable energy from wind and solar. But I will say wind and solar are not going to do it. They cannot meet the United States energy demands by even 2050, forget the global energy demands. So I am increasingly convinced that we have to do what is called carbon capture and storage. And the reason I'm talking about this is because some people call that geoengineering. But what we're talking about here is, you take a coal or a natural gas fired power plant, and instead of releasing that CO2 in the atmosphere, you trap it at the smokestack, and then you put it back in the ground where it came from. And the way I see it is that this isn't, a whatever you want to call it, a war on oil or a war on coal. I see it as a war on CO2. We have to do whatever we can do to reduce CO2, and of course, not just in this country, but globally. And so if I were president right now, I would put a ton of money into renewables. I would also continue to push nuclear, which is contentious with many environmentalists, but it is basically a carbon-free energy source, which is well tested and tried and true. You just don't put it in tsunami or earthquake-prone areas. But I would do that, and then I would spend a ton of money investing in carbon capture and storage, which some people would call like clean coal. Like I said, it's a war against CO2, not necessarily a war against coal. And especially when you look overseas, you look at how many coal-fired power plants the Chinese are building today, right? They build over 100 of them every year, all right? Every 3 days there's a new one opening. And so those have 50-year lifetimes. If China burns all that coal with all those power plants, we're in towards that business as usual scenario, right? And things are not where I at least hope that we end up. So, those coal-fired power plants are going to be there. We have to capture that carbon and put it back in the ground. And the reason I'm very excited about that solution as part of the mix, along with more renewables, is that, the people who benefit from that are the sort of existing energy industry that exists out there. That multi-trillion-dollar fossil fuel industry has to be a part of the solution. I don't see a politically viable solution that basically says to the Exxon Mobils and the BPs and Shells of the world, sorry folks, we're done with you. So I imagine a future where we continue to pay Shell, BP, and everyone else, all these other fossil fuel companies, to continue to take fossil carbon out of the ground. But then when we burn it, we trap that CO2, and we pay these companies to put it back in the ground. And as soon as these companies see this as a economic potentially even an economic win-win, we pay you to take it out, we pay you to put it back in. I think then politically we could see some movement, at least in this country. And that's why I would really push that, because I think it's a potentially what we would call politically bipartisan solution that people on both sides of the aisle can get behind. What's interesting is that oil companies already do this. They already pump CO2 back into the ground. They just do it to get more oil out of the ground. But it's a nice byproduct that CO2 stays down there. So that's how I see our future. And I'm convinced that we, in the near future, will need to start pumping CO2 directly out of the atmosphere using some technology. And some prototype technologies exist. They're just not cost effective yet. So, but I see a future where we continue to get fossil fuels, we just trap that CO2, we put it back in the ground, and we actively pump CO2 out of the atmosphere, and we increase our renewables, and we reduce our energy use. That's the best I can do in a couple minutes.
Okay, well, thank you. We've got a few more minutes for questions. I have a question from Hillary. Can you unmute, Hillary, and ask your question?
Yes. Hi, everyone. I read an article recently about the thawing in the Arctic tundra in a lake that was bubbling methane. And I'm wondering if there has been much research about that. I couldn't tell from the article sort of what studies were happening related to either the general Arctic thawing. I think there's been some about that, but about these sort of trapped gases that might be coming up through lake bottoms. Thank you.
Yeah, that's a great question. There's a lot of work going into this. So there's a ton of carbon, mostly in the form of methane, that's trapped in the permafrost, up particularly in northern Canada and Siberia. And so there's a concern that as you thaw that permafrost, which is happening, that you release a bunch of methane and you accentuate CO2, and it's one of those positive feedback cycles that can accentuate warming. So there's a lot of people researching this. What's really interesting is that I'll just give you the quick Cliff Notes version is I'm not hugely concerned about this. I'm not hugely concerned about this because when we look in the past at other times when the Earth was naturally, a little bit warmer than today, we don't see that happening. We don't see a big spike in methane suddenly occurring. What we are finding is that when the permafrost thaws, you get all this new microbial activity, new bacteria and archaea that start to thrive in those, now you would call them soils instead of permafrost, and they actually can feed on that methane. And so it's actually unclear how much of that methane will get released to the atmosphere. So it's an active area of research. It's super interesting. Lots of smart people are working on it. And while there is some concern and it makes for nice headlines, it's not keeping me up at night as much as say what we're choosing to do with our CO2 emissions.
Okay, great. Dave, you raised your hand and I think you have a question. You want to unmute?
Hi, everyone. Yeah, sure. Seen a lot of reports, heard a lot of reports lately in this current political environment about federal climate data being scrubbed from websites like the EPA or others. And I'm wondering if you've been impacted by that or seen any impacts as a result of that, or have any other comment about it.
Yeah, really interesting question. So the data that the federal government has an amazing repository of climate and weather data. So the National Weather Service, the National Climate Centers, NOAA, and NASA, they have amazing repositories of data. I have not personally seen any evidence that those data are being manipulated or scrubbed or anything like that. There was a huge push just as the current administration took office to back up that data on as many independent servers as possible. And I know that did happen. I think that was probably a little bit silly, but why not? It didn't take much effort to do. So, okay, sure. But I have not seen I've not had any impacts from it. We do work with those data, as I showed you with the extreme precip. We've never had any problem getting data. I do know that, they're scrubbing the terms climate change from a lot of these websites, and a lot of pages that I used to use for my teaching say on the EPA website or on the NOAA website, they're gone. And so that is pretty striking to me. I mean, it's clear that they're trying to reduce conversation about that term, climate change. But in terms of the data sets themselves, I haven't seen an impact.
Okay, it's about time. Eric, I want to really thank you for taking your time, and thank your children for being so quiet.
Yeah, they were good.
They were good.
I'm gonna go give them a cookie.
I already had some requests. Is it possible to get a PDF of your slides?
Yeah.
If you send them to me, I can get them out to the people.
Yeah, that won't be a problem.
Okay. Thanks again, and thanks everyone for joining. Hope to see you at a UVA meeting, Eric.
All right. We'll see you
Okay.
soon, Michael. Thank you, folks.
Okay, bye-bye.
Thank you, guys.
Thank you.